There has been significant hype around machine learning and artificial intelligence over the past decade. From small startups in Silicon Valley to the public sector, AI offers the next significant opportunity for process automation and optimization. Anyone with a smartphone encounters AI hundreds or thousands of times a day. AI is deeply embedded in photo applications, social media apps, payment processing, food distribution, and financial applications. Every ad you see online is the result of an AI building your demographic profile to optimize revenue for the advertiser and platform. This very article itself was composed using AI-powered writing augmentation tool that suggests grammatical improvements, rewrites sentences, and reports an AI-powered score on how readable the content is. With success in the consumer sector and new computational tooling, AI is now embedded in the corrosion and pipeline integrity business, promising rapid improvements in monitoring technology, risk assessment, and corrosion detection. Especially when paired with the Internet of Things sensors, the promise of AI is real-time cathodic protection monitoring. At the atomic level, artificial intelligence is an algorithm, a process which takes an input and produces an output. That input can be anything: a picture of your dog, the sentence, a photo of a segment of pipe, or an inline inspection assessment. The output can also be anything: another picture, or a probability, or even a corrosion growth rate estimate. This approach may sound familiar. The entire field of statistics is devoted to composing models to estimate one thing as a function of something else. There are over 50 years of papers in Nace and the corrosion literature using statistics. What makes this round of AI novel? The short answer is a process called automated feature selection. In the past, an analyst or researcher would identify features they suspect would cause corrosion, plug those variables as inputs into some statistical test, and get a result. With AI, researchers take every variable they can get. In the case of corrosion, not just pipeline features, but atmospheric features, human-like activity like road salts, and soil parameters. They throw the kitchen sink at the algorithms, which then build their internal structures of which features matter and how they interact. If you've heard the buzzword big data, this is why big data matters. It is now the input into massive AI algorithms. Simultaneously, academic researchers and governmental agencies have been prolifically sharing massive geospatial datasets reporting soil conditions, atmospheric conditions, power lines, pollution, among other things. These datasets are very high resolution in hard-to-use formats, but incredibly valuable for researchers using AI. These trends converge in the pipeline industry with Mazzella, Nace 2019 and 2020, and Hayden, Nace 2021. In all 3 years of the papers, they used the corrosion growth rate estimates collected from ILI from a North American pipeline operator and developed machine learning algorithms to estimate risk. In all cases, they were able to establish an accuracy rate of over 95% in predicting the corrosion growth rate for the underground pipeline. They compared and contrasted different modeling technology and found, at least in the cases presented, that an algorithm called XGBoost showed the best result. This result is not surprising. XGBoost performs well on many problems across many industries and is popular on the AI competition website Kaggle. Unlike traditional statistics, the downside to using these AI algorithms is that the model itself is challenging to interpret. There is no simple way to gaze into the AI and understand what it is doing. In this sense, the algorithms are like black box. The trade-off is high performance, but in exchange, the researchers lose the ability to answer why. Without the answer to that question, it is difficult to detect bias, find mistakes, and build a casual understanding of corrosion mechanisms. This is an active area of research in machine learning space and addressed in work recently accepted to Nace 2021. The second challenge to using AI is making it useful to corrosion experts in the field. It is one hurdle to generate a corrosion growth rate estimate, but a much harder problem making the predictions usable to professionals out in the field. For this, we built geospatial tools to allow users in the field to search for a location, view the feature and growth rates of that location, and identify potential corrosion features. The most significant improvements in AI algorithms in the last decade have been on computer vision tools. Computer vision algorithms specifically take photos as input and can output anything: information on the images, people identified in them, or the degree of corrosion visible, along with locations and severity. This technology will revolutionize the corrosion inspection industry by augmenting manual inspections or replacing them altogether, allowing more frequent automated scans. For this to work, an enormous data set needs to be compiled of corrosion in a variety of settings, not just in pipeline environments. For this, Nace has helped organize SP 21467, a technical workgroup devoted to amassing an industry-wide open-source collection of labeled corrosion images for computer vision use. A proof of concept of the technology is available for download at download.osr.ai. AI has the upside potential to dramatically improve many of the hurdles faced by those in pipeline integrity. It can deliver the promise of improved safety, compliance, and efficiency from slow cycles on observing and estimating corrosion to real-time scans of assets.